Welcome to this coding walkthrough. Today, we'll be tackling LeetCode problem number 1616, split two strings to make palindrome. In this problem, we'll explore how to determine whether it's possible to split two strings at some index to form a palindrome. Let's dive in and break it down step by step. In this problem, you are given two strings, A and B, both of the same length. Your task is to determine if it is possible to form a palindrome by splitting and recombining parts of these two strings. Here's how the process works. You can choose a non-negative integer k, where k can range from 0 to the length of the strings. Using this k, you split string A into two substrings, A_left, which is the first k characters, and A_right, which is the remaining characters. Similarly, you split string B into B_left for the first k characters and B_right for the rest. Then, you combine A_left with B_right to form a new string. If this new string reads the same forward and backward, meaning it's a palindrome, you return true. Otherwise, you return false. A palindrome is a string that mirrors itself, such as racecar or madam. The inputs A and B will consist only of lowercase English letters, and the length of each string can go up to 100,000 characters. Your solution must handle this efficiently. The output is a simple Boolean value, true if creating a palindrome is possible, and false otherwise. To understand this better, let's look at an example. Consider the inputs A equals X and B equals Y. Here, both strings are of length 1. If we split both strings at k equals 0, A_left and B_left will be empty strings, while A_right will be X and B_right will be Y. When we concatenate A_left with B_right, we get the string Y. Since Y reads the same forward and backward, it's a palindrome, and the output is true. This example demonstrates that even the smallest strings can be checked for this property and that the result depends on the split point and the resulting concatenation. Now consider another example where A equals abdef and B equals fcab. Here, we can split both strings at k equals 2. This means A_left will be ab and A_right will be def, while B_left will be fe and B_right will be cab. Concatenating A_left with B_right produces the string abcab. If you check this string, it matches when read forward and backward, making it a palindrome. Therefore, the output in this case is also true. This example highlights how the choice of k plays a critical role in creating a palindrome, and it illustrates that the operation can work even with longer strings. For another example, let's take A equals ulakt and B equals jazalu. Splitting these strings at k equals 3 gives us A_left equals ula and A_right equals cfd, while B_left equals jiz and B_right equals alu. When we combine A_left with B_right, we get the string ulelu. This string reads the same backward as it does forward, so it's a palindrome. As a result, the output is true. This shows that even with more complex strings, the method of splitting and recombining can successfully form a palindrome. It's important to note that the algorithm needs to explore different values of k to find the right split point. There are some constraints and edge cases to keep in mind. First, the lengths of A and B are always equal, and they can range from 1 to 100,000 characters. Both strings consist only of lowercase English letters. One edge case to consider is when the strings are only one character long, like A equals A and B equals B. In this case, the result is always true because any single character is inherently a palindrome. Additionally, if either A or B is already a palindrome, the result will also be true, regardless of how they are split. On the other hand, for cases where no split can produce a palindrome, such as A equals ABC and B equals XYZ, the result will be false. Finally, since the input size can be very large, up to 100,000 characters, the solution must be efficient to handle these cases within a reasonable time frame. To solve the problem of splitting two strings to form a palindrome, we need to explore potential strategies. The first approach we might consider is a brute force method. The idea here is to try every possible split point in the strings, from index 0 to the length of the strings. For each split point, we would check if concatenating the first part of one string with the second part of the other forms a palindrome. To determine if a string is a palindrome, we can compare its first half to the reverse of its second half. While this approach is straightforward and easy to understand, it requires slicing and concatenating strings at every possible split, followed by a palindrome check for each case. This results in a time complexity of O(n squared, which becomes impractical for longer strings since the problem allows input sizes up to 10 to the power of 5. Therefore, while conceptually simple, this method is inefficient and unsuitable for larger inputs. To address the inefficiencies of the brute force method, we consider an optimized approach using the two-pointer technique. This method avoids explicitly checking all possible splits. Instead, we use two pointers, one starting at the beginning of the strings and the other at the end, and move them inward while comparing the characters at each position. If a mismatch occurs, we then examine two possibilities, replacing the mismatched section with the corresponding prefix or suffix of one string and checking if the result forms a palindrome. A critical observation here is that for the split to work, the substring of one of the strings on the mismatched side must itself be a palindrome. This eliminates the need for unnecessary slicing and concatenation, significantly improving efficiency. The two-pointer approach operates in O(n) time, making it far more scalable. It is chosen for its ability to handle large inputs efficiently while avoiding the overhead of unnecessary operations, which makes it a clear improvement over brute force. The optimized two-pointer technique emerges as the most effective strategy for solving this problem. By leveraging the properties of palindromes and eliminating redundant operations like slicing and concatenation, this approach ensures efficiency. We begin by placing two pointers at the start and end of the strings, moving them inward until a mismatch is found. At the point of mismatch, we evaluate whether replacing the mismatched section with the prefix or suffix of either string produces a palindrome. If either option succeeds, we return true, otherwise, false. This method is not only time efficient, with a complexity of O(n), but it also handles edge cases gracefully, such as when the strings are already palindromic. Furthermore, it minimizes memory usage by avoiding recursion or additional data structures. While the brute force method is simpler to implement and recursive solutions may seem elegant, both fall short in performance. The two-pointer approach strikes an ideal balance between clarity and efficiency, making it the optimal solution for this problem. To solve this problem, we aim to determine if we can split two given strings, A and B, at some index k so that the concatenation of their respective parts forms a palindrome. A palindrome is a string that reads the same forwards and backwards, such as ABBA or Recursion. The challenge lies in efficiently identifying this split point and verifying the palindromic combinations. The process begins with understanding how to check if a string is a palindrome. A string is palindromic if its characters symmetrically mirror around the center. For instance, in Recursion, the first character matches the last, the second matches the second to last, and so on. To verify this, we can compare the string's first half with the reversed second half. Next, we move to splitting and combining the strings. For a given index k, we split A into A, 0 k, and A, k, and similarly split B into B, 0 k, and B, k. We then test the combinations A, 0 k, plus B, k, and B, 0 k, plus A, k to see if either forms a palindrome. Identifying a valid split requires checking these combinations for all possible indices k. To optimize this process, rather than checking every possible split through brute force, we can use the two-pointer technique. This strategy significantly reduces redundant computations. Here's how it works: we use two pointers, one starting at the beginning of the strings, I equals 0, and the other at the end, j equals n1. We then compare characters from A and B at these positions. If A, I matches B, j, or B, I matches A, j, we move the pointers inward by incrementing I and decrementing j. This ensures we only check the critical parts of the strings. However, if a mismatch occurs, we have two options. We can check if the remaining portion of A, specifically A, I, j plus 1, forms a palindrome, or we check if the corresponding portion of B, B, I, j plus 1, is palindromic. If neither is true, then the split at this point is invalid. To implement this, we define a helper function as _palindrome, s, to verify if a given string s is a palindrome. The main function, check_palindrome, a, b, uses the two-pointer technique to identify mismatches, calling is _palindrome on the remaining substrings as needed. If any valid split is found, the function returns true. Otherwise, it returns false after checking all possibilities. The two-pointer technique is a crucial insight that enables us to avoid unnecessary computations. By directly comparing characters from both ends, we can stop early when mismatches occur, focusing only on the relevant portions of the strings. Instead of explicitly splitting the strings, we dynamically slice substrings, which is more efficient for palindrome checks. This optimization ensures that we only check substrings when mismatches happen, saving time compared to a brute force approach that tests all possible splits. Key data structures include the two pointers, which dynamically reduce the problem space as they move inward, and string slicing, which allows us to extract and verify substrings for palindromes. While slicing is efficient in Python with an O(1) operation for indexing, creating new substrings can increase memory usage slightly. Analyzing the algorithm's complexity, the time complexity is O(n), where n is the length of the strings. Each character is inspected at most once using the two-pointer approach. The space complexity is O(n), stemming from the slicing and temporary substrings created during the palindrome checks. This balance of time and space efficiency makes the algorithm well-suited for solving this problem. When applying this approach, it is important to account for edge cases. For example, if either string A or B is already a palindrome, the problem becomes trivial because no splitting is required. Similarly, there may be cases where no valid split exists, such as when the strings have entirely mismatched characters, like ABC and def. Another edge case involves strings of unequal lengths, though the problem guarantees that A and B will always have equal lengths. By carefully handling these scenarios, we can ensure the algorithm is robust and produces correct results in all cases. This implementation solves LeetCode problem number 1616, split two strings to make palindrome. The task is to determine if two given strings, A and B, can be split at some index such that the concatenation of one prefix and the other suffix forms a palindrome. The solution involves 1. Helper function, check_palindrome. This function checks if a string is a palindrome by comparing it to its reverse. It is used extensively to validate if a substring is a palindrome. 2. Helper function is _palindrome_possible. This function examines whether we can split two strings, A and B, such that the resultant concatenated string forms a palindrome. It uses two pointers, left and right, to traverse the strings. If a mismatch occurs between A, left, and B, right, we check both possible splits at the mismatch point. A, left to right +1, substring from A to complete the palindrome. B, left to right +1, substring from B to complete the palindrome. If either split forms a palindrome, the function returns true. Otherwise, it continues checking. 3. Main function, check palindrome formation. This function is the entry point of the solution. It calls is_palindrome_possible twice. Once with A as the prefix and B as the suffix. Another time with B as the prefix and A as the suffix. If either combination produces a valid palindrome, the function returns true. ###time complexity. The solution operates in O(n) time, where n is the length of the strings, as it involves a single traversal with two pointers. ### space complexity. The space complexity is O(1), since no extra data structures are used. This implementation is efficient, clean, and handles all edge cases, including empty strings and strings that are already palindromes. Here, we start by defining a helper method called checkPalindrome. This method checks if a given string is a palindrome by using two pointers, left and right. These pointers start at the beginning and end of the string, respectively, and move toward each other. If at any point the characters at these positions are not equal, the method immediately returns false. Otherwise, if the loop completes without finding any mismatches, the method returns true, confirming the string is a palindrome. Next, we have another helper method, isPalindromePossible, which takes two strings, A and B, as inputs. This method uses a two-pointer approach again, with left starting at the beginning of both strings, and right starting at the end. As the pointers move, if a mismatch is encountered between A.char at left and B.char at right, it checks whether the substring from the current position in either or B forms a palindrome. This is achieved by calling the checkPalindrome method on the respective substrings. If either case results in a palindrome, the method returns true. If no mismatches are found during the traversal, isPalindromePossible finally returns true, indicating that it's possible to form a palindrome by combining the two strings. Now, we move to the main method, check palindrome formation, which takes two strings, A and B, as inputs. This method determines if a palindrome can be formed by splitting A and B in either order. It does so by calling isPalindrome possible twice, first with A and B as arguments, and then with B and A. If either call returns true, it means a valid split exists, and the result is true. Otherwise, it returns false. This ensures that every possible split is checked, and the implementation is both efficient and straightforward. To begin, we'll look at the simplest case where both strings are just one character long, A equals X and B equals Y. The function check palindrome formation starts by calling is_palindrome_ possible, A, B. Inside this helper function, we initialize left and right pointers to 0 because the length of the strings is only 1. The while loop condition left-right is immediately false since both pointers are at the same position. This means there's no opportunity for mismatches, so the function concludes that a palindrome can be formed and returns true. Consequently, the main function also returns true. The reasoning is straightforward, single-character strings are always palindromes by definition, so the output is true. Now let's analyze a slightly more complex example with A equals abdef and B equals fcab. The main function first calls is_palindrome_ possible, A, B. Here, left starts at 0 and right at 4, the last index of the strings. The first comparison is between A, 0, A, and B, 4, B, which don't match. At this point, we check if the substrings A, left to right plus 1, or B, left to right plus 1, are palindromes. The substring A, 0:5, or abdef is not a palindrome, and neither is B, 0:5, or fcab, so this call returns false. Next, the function checks the reverse configuration by calling is_palindrome_ possible, B, A. This time, B, 0, F, matches A, 4, F, so we move the pointers inward. B, 1, E, matches A, 3, E, as well. When the pointers meet at left equals 2 and right equals 2, the remaining substring is confirmed to form a palindrome. As a result, this call returns true, and the main function concludes that a valid split exists, returning true. In this final example, we have A equals ulakt and B equals jazalu. The main function begins by evaluating is_palindrome_ possible, A, B. Initially, left is 0 and right is 5. The first characters, A, 0, U, and B, 5, U, match, so the pointers move inward. The second characters, A, 1, L, and B, 4, L, also match, and the pointers continue converging. Next, A, 2, A, and B, 3, A, are equal, and now left surpasses right at left equals 3 and right equals 2. This confirms that the remaining substring forms a valid palindrome, so the helper function returns true. The main function then concludes that a valid palindrome can be formed by merging these strings, and the final output is true. The reasoning here is that every character at corresponding positions matched, ensuring the entire string pair contributes to a palindrome. To analyze the time complexity of this solution, let's break it down into the constituent operations. First, we have the check_palindrome function. This function works by reversing the string and then comparing it to the original. Reversing a string of length n takes O, n, time, so each call to this function contributes O, n. Next, in the is_palindrome_ possible function, we use a two-pointer traversal of the strings A and B. The while loop iterates over the strings, moving the left and right pointers inward. In the worst case, this traversal will run for half the length of the strings, which is O, n/2, and this simplifies to O, n. If a mismatch between the strings is found, the function performs two additional palindrome checks on substrings. Each of these substring checks calls check_palindrome, which takes O, n. So, in the worst case, the two checks add up to O, n, plus O, n, equals O, n. Combining this with the traversal, the total time complexity for is_palindrome_ possible becomes O, n. Finally, the check palindrome formation function calls is_palindrome_ possible twice, once with A, B, and once with B, A. Since each call is O, n, the total time complexity of the main function is O, n, plus O, n, equals O, n. Now, let's look at the space complexity. The solution has an overall space complexity of 1, as no additional memory is allocated that scales with the input size. In the check_palindrome function, a reversed copy of the string is created, which requires n space temporarily. However, this space is tied to the substring being processed, not the full input, and does not persist beyond the function call. Importantly, no additional data structures are used here. In the is_palindrome_possible function, we use two pointers, left and right, which require only 1 space. Similarly, the check palindrome formation function does not allocate any extra memory beyond what is already used internally in the calls to is_palindrome_possible. Since no recursive calls or dynamic data structures are involved, the overall space complexity of the solution remains constant at 1. Let's discuss the best, average, and worst-case performance of the algorithm. In the best-case scenario, the strings are already palindromes. Here, the two-pointer traversal in is_palindrome_possible terminates early after n/2 iterations. While the time complexity is still n, the constant factors involved are lower due to the early termination. For the average case, we expect random strings where mismatches might occur. The algorithm will detect these mismatches and perform substring palindrome checks as needed, but the time complexity remains n overall. In the worst case, the strings require a full traversal and substring checks for palindromes. This still results in n time complexity, as the palindrome checks dominate. To put this in perspective, a brute force approach would involve generating all possible splits of A and B, resulting in n² combinations. For each combination, checking for a palindrome would take n, leading to an overall time complexity of n³. By using the two-pointer traversal and early exits, the proposed solution reduces this dramatically to n, making it far more efficient. The linear complexity comes from the two-pointer traversal and palindrome checks, both of which are linear operations. Additionally, the absence of recursive calls or memory-intensive data structures reinforces the efficiency of this approach. When solving this problem, there are several common mistakes to watch out for. First, it's essential to evaluate both split combinations, A, 0k, plus B, k and B, 0k, plus A, k. Focusing on just one of these can lead to missed solutions. Second, edge cases like empty strings, single character strings, or situations where A and B are already palindromes can easily be overlooked, so make sure to test these thoroughly. Another mistake is inefficient palindrome checks, where repeatedly using an n loop can slow things down unnecessarily. Instead, creating a helper function for these checks can make your solution more efficient. Early termination is another critical optimization. Once a valid split is found, there's no reason to continue processing. Finally, be cautious with string slicing, as off-by-one errors or incorrect slicing logic, such as confusing a k with a 0k, can lead to subtle bugs. Double-checking slicing operations is a good habit to develop. Now, let's dive into some key insights for interviews. Palindromes are fundamentally symmetric, so mismatched characters at the boundaries of strings A and B can guide your decision to switch between their prefixes and suffixes. This symmetry is crucial for narrowing down potential splits. To efficiently solve the problem, a two-pointer approach is ideal. By comparing characters from the start and end of the strings, you can achieve linear time complexity, avoiding redundant computations. During an interview, it's also important to articulate the trade-offs of this approach compared to brute force. Highlight how the two-pointer method eliminates unnecessary checks while maintaining clarity. Additionally, always clarify edge cases with your interviewer, whether it's handling empty strings, single character inputs, or scenarios where the strings are already palindromes. This demonstrates a thorough and thoughtful approach to problem solving. Several related problems can help reinforce your understanding of palindrome patterns. For example, LeetCode 125, Valid Palindrome, focuses on simple palindrome validation, while LeetCode 680, Valid Palindrome 2, involves checking palindromes with one character removal. LeetCode 131, Palindrome Partitioning, explores splitting strings into multiple palindromes, which introduces recursive strategies. Finally, LeetCode 214, Shortest Palindrome, challenges you to construct the shortest palindrome by adding characters to the string. These problems are excellent for practicing key techniques like the two-pointer approach and recursion, which are frequently used in palindrome-related problems. They also provide valuable insight into how these concepts can be extended to more complex scenarios. There are also alternative approaches you may encounter or consider. A brute force method involves trying all possible split points k and checking both combinations, a, 0 a k, plus b, k and b, 0 a k, plus a, k. While simple and easy to implement, this approach has a time complexity of O(n squared, making it unsuitable for larger inputs. A more efficient solution is the optimized two-pointer approach. Here, you start with pointers at the boundaries of the strings and move inward, checking for mismatches. If a mismatch occurs, you evaluate the two possible splits without recomputing the entire substring. This method achieves linear complexity and is highly efficient, though it requires careful handling of mismatched characters. Another alternative is a recursive palindrome check, which dynamically validates palindromes while splitting the strings. While useful for practicing recursion, this approach is less optimal due to its overhead and potential stack overflow for large inputs. Each method has its trade-offs, so understanding their advantages and limitations will help you choose the best approach for a given scenario. Great job! To summarize, we've tackled the problem of splitting two strings to form a palindrome, discussed the algorithmic approach, and highlighted key takeaways. Thanks for watching, and don't forget to like, share, and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!